Section 1 Introduction. We're here to talk about the evolution and challenges of large language models, LLMs, such as the Generative Pre-trained Transformer, GPT, models. These models have become increasingly powerful, with the transition from GPT-3 to GPT-4 and the introduction of other LLMs like PaLM and Llama. These models have shown significant improvements in understanding and solving problems in natural language. They're used in a variety of fields, creating information for many applications. However, there's a major issue with these models when it comes to applications that need high accuracy and reliability, like in the biomedical and healthcare sectors. This issue is known as hallucination, where the model generates information that isn't based on the input data. Unfortunately, we don't have efficient tools to identify hallucination or to estimate the confidence level of the output. The confidence score provided by the LLMs is often not available or not well calibrated, especially after reinforcement learning with human feedback is applied. There are two main ways to assess the confidence level of LLM responses. The first is internal evaluation, where the LLM is prompted in different ways to produce multiple responses. These responses are then used to infer the reliability of the answer. However, these methods are less quantitative and can be biased by the model itself. The quality of the results can also depend heavily on the prompting strategy, and there's no systematic way to quantify this. The second approach involves using external sources of information, like human reviewers or large-scale labeled data to build evaluation models. These methods require a lot of manual annotation, which is time-consuming and expensive. This is one of the main obstacles in modern supervised model training. As a result, self-supervision, which uses patterns within the data and knowledge from external sources, is a promising alternative. Drawing inspiration from previous works in programmatic supervision and Pareto optimization, we propose a flexible framework that combines information from both the LLM response and supervision sources using Pareto optimal learning. This approach is based on two main ideas. First, we need external supervision sources that are independent of the LLM to avoid bias. Second, if we consider the LLM errors as noisy disturbances on the correct labels, fitting a model with LLM noise and independent external noise can help improve calibration power. In this context, Pareto optimal self-supervision serves as a great framework to incorporate both features. It's important to note that this approach only requires unlabeled data, making it applicable to areas where annotation is expensive. Our main contribution in this paper is a new framework for LLM calibration through Pareto optimal self-supervision. We introduce the Pareto optimal learning assessed risk, POLAR, score for estimating the LLM error probability. We've tested this on 4 different natural language processing tasks and found that the POLAR score is well calibrated and highly correlated with the LLM error rate evaluated on correct labels. We've also improved LLM performance using dynamic prompting techniques for high-risk instances as identified by the POLAR score. We've shown that this technique can correct LLM errors and boost the performance of a GPT-4 baseline model to outperform the current best supervised model, without using any human-labeled training data. Section Summary. Large language models, LLMs, like GPT-4 have shown significant advancements in natural language understanding and problem-solving abilities. However, the challenge of hallucination remains when LLMs are applied to domains that require high accuracy and reliability. Existing methods to assess confidence levels are either biased or require manual annotation efforts. To address this, we propose a framework called Pareto optimal self-supervision, which combines information from LLM responses and external supervision sources. Our approach, POLAR, estimates LLM error probability and improves LLM performance without using human-labeled training data. Section 2 Related work. The section begins by discussing previous research in the field of model calibration. The earliest work in this area was Platt scaling, which involved fitting a logistic calibration model on top of the original model output. Since then, various techniques have been developed for model calibration, including isotonic regression, temperature scaling, and Bayesian binning. A method for calibrating language model, LM, was proposed that adjusts the class balance by using a group of LM queries with content-free input. As calibrating LMs accurately is difficult, a heuristic method known as self-consistency was developed to estimate the confidence of an LM in its response. Most of these calibration methods rely on labeled calibration data, and there isn't a systematic self-supervised approach that we know of. Our work involves combining multiple supervision sources in the absence of training labels. This approach has been widely studied in the field of programmatic weak supervision. Following early works in distant supervision and crowdsourcing, data programming was proposed to systematically combine weak labels. Many methods have been developed in this field, with METAL, now known as Snorkel, being a popular method. Most of the existing works assign fixed weights to all the sources across all the examples, which will be dominated by the LM and fail to capture the small amount of examples where the LM is likely to be wrong. We address this problem with Pareto optimization to be adaptive to all sources simultaneously and show that this approach offers better LM calibration compared to Snorkel. In the next section, we propose a flexible framework of Pareto optimal learning that can be adapted to any LM-based prediction task. We then present the formula to calculate the risk indicator score to evaluate the confidence of an LM response, which we refer to as the polar score. Consider the joint distribution on the input-output pair space. The general workflow of prompt-based LM works as follows. For any input example with a specific prompt setting, the LM first generates a free text response. The free text response is then projected by an operator onto the desired output space, plus an abstain option. The abstain option refers to any case where the free text response is not clear enough to fit into any element in the desired output space, for example, when the LM is unsure about the answer. In general, we want the LM to give a clear response if possible, and state unsure when it is not confident about the response. However, even when well-designed prompting strategies are used to achieve this goal, the problem of hallucination still remains, where the model confidently states an answer that is actually wrong. The goal of LM calibration and hallucination detection is to develop a risk indicator function that estimates the true probability of hallucination. In this paper, we derive the risk indicator function using self-supervision, in which setting, we have access to n labeled training examples with ground truth outputs completely unavailable. In addition, a human expert can specify m supervision functions that can be triggered to give heuristic or noisy outputs. The output 0 refers to an abstain output where the supervision function is not triggered to assign a label. Unlike LMs, each supervision function is usually triggered on only a very small portion of data. Even on examples for which they assign labels, supervision functions are only required to be weak supervision sources, with the typical theoretical requirement that the assigned label is better than a random guess. In practice, the supervision functions can be as simple as keywords, regular expression, or knowledge-based querying. The details are discussed in the following section. Section Summary. Early works in model calibration, such as Platt scaling, focused on fitting a calibration model on top of the original model output. Various techniques have been developed since then, including isotonic regression, temperature scaling, and Bayesian binning. However, most of these methods rely on labeled calibration data, and there is currently no systematic self-supervised approach. In this paper, we propose a flexible framework called Pareto optimal learning that can be adapted to any language model-based prediction task, and we introduce a risk indicator score called the polar score to evaluate the confidence of a language model's response. Section 3.2 Pareto optimal learning. In our approach, we use a model, which we call a harmonizer, to map from a set X to a set Y. This model is designed to align with both the responses from the latent language model, LLM, and the supervision functions that we manually specify. To achieve this, we need to solve an optimization problem. This problem involves minimizing the expected value of a function, which we denote as L_0, that measures the difference between the output of the harmonizer and the output of the LLM or the supervision functions. However, this problem can be complex because the objectives of the LLM and the supervision functions may conflict with each other. To address this, we use a concept from multi-objective learning theory called Pareto optimality. A harmonizer is Pareto optimal if there is no other harmonizer that performs better in all objectives. In other words, a Pareto optimal harmonizer is the best compromise between the conflicting objectives. To find a Pareto optimal harmonizer, we propose to use a loss function that aggregates the losses from all sources. This function, which we denote as G, takes as input the losses from the LLM and the supervision functions and outputs a single value. We require this function to satisfy two conditions. It should decrease when any of the input losses decreases, and it should be convex. In our experiments, we tested 4 different types of this function: a linear function, a quadratic function, a function based on the Euclidean norm, and a function based on the Chebyshev norm. Each of these functions is weighted by a set of parameters, which we denote as W_J. We found that the first 3 types of functions satisfy the conditions for a Pareto scalarizer, while the last one does not. However, we included the last one for comparison purposes. We have proven that our approach is guaranteed to find a Pareto optimal harmonizer. The proof involves 2 steps. First, we use a mathematical inequality called Jensen's inequality to simplify the problem. Then, we use the definitions of Pareto optimality and the Pareto scalarizer to prove that our approach works. In our experiments, we found that a suitable Pareto scalarizer automatically balances the output from the LLM and the supervision functions. We will discuss the method to automatically determine the weights W_J in the supplementary materials. Section Summary. The proposed method introduces a harmonizer model that is fit in the semantic space to simultaneously align with both the LLM responses and manually specified supervision functions. To solve the optimization problem with multiple conflicting objectives, the authors propose finding a Pareto optimal harmonizer that minimizes losses on all sources. They explore different types of scalarization functions, such as linear, quadratic, Euclidean norm, and Chebyshev, to approximate the Pareto optimal solution. Section 3.3 Polar Score. We suggest a method to improve the calibration of our harmonizer model. This involves using a type of loss function known as cross-entropy loss. We then use algorithms like stochastic gradient descent, SGD, or ADAM to solve the problem. Once we find the best solution, we define a score called the Pareto Optimal Learning Assessed Risk, Polar, score. This score is a measure of the risk of a new response from the language learning model, LLM. We also propose two strategies to correct errors in the LLM responses using the Polar score. The first strategy is dynamic self-examination. Here, if the Polar score exceeds a certain threshold, we ask the LLM to reconsider its answer. The second strategy is dynamic self-supervision. In this case, we use supervision functions to help the LLM review its initial response. We tested our approach on 4 different natural language processing (NLP) datasets: CDR, ChemProt, SEM-Eval, and SMS. We removed the labels on the training sets and used the gold labels on the test sets for evaluation. We chose these datasets to cover a range of domains, tasks, and difficulty levels. For instance, the SEM-Eval and SMS datasets are from the general domain, while the CDR and ChemProt datasets are from the biomedical domain. The tasks include relation extraction and classification. The difficulty varies from tasks that are easily solved by advanced LLMs like GPT-4, such as SMS, to tasks that are still challenging for GPT-4, like CDR, ChemProt, and SEM-Eval. Section Summary. The Polar score is used to assess the quality of calibration in the harmonizer model by utilizing cross-entropy loss functions and stochastic gradient-based algorithms. It helps identify high-risk LLM responses, allowing for the implementation of dynamic prompting strategies to correct errors. The experiments conducted on various NLP datasets demonstrate the effectiveness of the Polar score in different domains, tasks, and difficulty levels. Section: Prompt Design. We've taken great care in crafting the prompts for each problem to fully utilize the potential of the large language models, LLMs. The structure of these prompts includes several elements. 1. Setting. We outline the LLM's role in the task and the overall problem context. 2. Background. We provide any necessary background knowledge for domain-specific tasks, including information from guidelines for human annotators. 3. Data structure. For tasks involving relation extraction, we clarify the definition of each entity. 4. Desired output. We detail the expected output and provide explanations and examples where necessary. 5. Chain of thought, COT. We include instructions to encourage the LLM to think and articulate its thoughts step by step, and to structure its response as desired. 6. Confidence. We instruct the model to express uncertainty if it's not confident about the answer. 7. Example. We provide an example and ask the model to perform the task. We also use supervision functions for the datasets, which are based on simple rules provided by human experts. These rules include keyword and regular expression pattern checking, querying knowledge bases like the Comparative Toxicogenomics database, and combining these methods hierarchically. In terms of training, we implement Pareto optimal learning as per a specific equation and algorithm. We experimented with different configurations of Pareto optimal learning, including 1. Harmonizer model. We tested 3 models: BERT, specifically PubMed-BERT for biomedical datasets CDR and ChemProt, multi-layer perceptron, MLP, and logistic regression, LR. The latter 2 models are built on top of the last layer embedding of the corresponding BERT model. 2. Pareto loss scalarizer. We experimented with all 4 loss scalarization functions defined in a specific section, namely linear, quadratic, Euclidean norm, and Chebyshev scalarization. 3. Optimizer. We use the ADAM W optimizer with a learning rate between 0.0001 and 0.000001, weight decay between 0.0001 and 0.00001, and a batch size of 16. All hyperparameters were optimized on a held-out development set. 4. Computation. We trained the models on Azure Standard North Carolina 12 SV3 with NVIDIA V100 GPU. The results we present in this section are limited to using BERT, PubMed BERT, as the harmonizer model and quadratic scalarization for loss scalarizer with equal weights. We further examine the contribution of different harmonizer models and Pareto loss scalarizers in a later section. Section Summary. In order to maximize the potential of language model-based methods, LLMs, we carefully design prompts for each problem, including the task setting, background knowledge, data structure, desired output, chain of thought, and confidence. The supervision functions for the datasets are based on simple rules provided by human experts, such as keyword checking and knowledge-based querying. During training, we explore different configurations of Pareto optimal learning, including different harmonizer models, loss scalarization functions, optimizers, and computational resources. The results presented in this section focus on BERT, PubMed BERT, as the harmonizer model and quadratic scalarization for loss scalarizer with equal weights. Section 4.1 Polar calibration of LLM error. In this section, we're going to discuss the results of our implementation of the algorithm. We used a fitted harmonizer on a new test set to generate a polar score for each LLM response. We then used the gold labels on the test set to calculate the actual error rate, as shown in the equation, and to assess how well the polar score aligns and correlates with the actual error rate. We used the GPT-4 model on the CDR chemical disease relation extraction task to demonstrate the calibration results of the polar score. The calibration curve shows that the polar score is a reliable predictor of the likelihood of the LLM making an error, as defined in the equation. The polar score is strongly correlated with the error rate, as shown in the figure. The figure also shows that the responses with the highest polar scores from all three different LLMs are the most likely to produce hallucinations or errors, with the highest polar scores indicating an almost 100% error rate. We evaluated the performance of the polar score in terms of LLM error calibration using two metrics: the expected calibration error, ECE, and the R-squared value between the polar score and the actual error rate. We tested this on all four datasets and three LLMs, GPT-4, GPT 3.5 Turbo, and Text DaVinci 003. We compared our results with four different baseline methods. 1. Snorkel. This method combines multiple sources of supervision through matrix completion. We trained the model on the training set, combining LLM response and supervision function outputs, and then used the class probability given by the model to estimate the LLM error rate on the test set. This method, formerly known as METAL, is highly recommended for weak supervision. 2. Majority vote. This method estimates class probability based on the voted ratios among the LLM and the supervision functions. This is another highly recommended method for weak supervision. 3. LLM distilled. Instead of learning from both the LLM and the supervision functions, we fit a BERT, PubMed BERT, model to the LLM output only. We then used the distribution from the fine-tuned BERT model to estimate the LLM error rate. 4. LLM ensemble. This method involves making multiple queries to the LLM and estimating class probability from the response ensemble. This approach is quite costly, so we only implemented it for GPT 3.5 Turbo on CDR. The resulting ECE was 0.4466, which is significantly higher than our proposed approach, so we didn't include it in the table to save space. Section Summary. In this section, the authors present the results of their algorithm implementation, which uses a fitted harmonizer to assign a polar score to each LLM response. They evaluate the calibration and correlation of the polar score with the actual error rate using gold labels on a test set. The results show that the polar score is a good estimator of the error probability, highly correlated with the error rate, and the responses with the highest polar score are most likely to generate errors. The performance of the polar score is compared with four baseline methods, and the proposed approach outperforms them in terms of error calibration. Section 4.2 LLM error correction with polar-assisted dynamic prompting. In this section, we delve into the use of polar-assisted dynamic prompting to correct errors in language model, LLM. We focus on the task of extracting CDR relations, using the GPT-4 and GPT 3.5 Turbo models, which are designed for conversational interaction. We use dynamic prompting strategies to reduce errors in the LLM. To demonstrate the significance of the polar score in these strategies, we rank the initial responses from the LLM based on their polar scores and calculate the error rate before and after dynamic prompting. Our findings show that the error rate of GPT-4 drops significantly when the initial response has a high polar score. However, if the initial response is deemed low risk, asking the LLM to self-check or providing self-supervision rules doesn't improve the outcome and may even raise the error rate. Therefore, it's best to use dynamic prompting only when the polar score is high. We implemented dynamic self-checking and dynamic self-supervision, setting the polar score threshold at 0.5. Both strategies improved the performance of the GPT 3.5 Turbo and GPT-4 models. With dynamic self-supervision, GPT 3.5 Turbo even surpassed the best result achieved without any gold-labeled training data, and GPT-4 outperformed the best supervised method that uses fully labeled data. It's worth noting that both strategies didn't use any gold-labeled examples. In the next section, we discuss the contribution of different components of our approach to error calibration. We believe that Pareto optimal self-supervision is the most crucial part of our approach. Keeping all other components constant, we compared the results of experiments using Snorkel and majority vote. Neither method consistently provided good calibration power, highlighting the importance of Pareto optimal self-supervision. Section Summary. In this section, the authors investigate dynamic prompting strategies to reduce errors in language model, LLM, responses. They focus on the CDR relation extraction task and experiment with GPT-4 and GPT 3.5 Turbo models. By sorting LLM responses based on their polar score, they find that dynamic prompting significantly decreases error rates only when the initial response has a high polar score. Dynamic self-examination and dynamic self-supervision strategies improve performance for both models, surpassing previous results without gold-labeled training data. The authors highlight the importance of Pareto optimal self-supervision in their approach to error calibration. Section. External sources of information. We use supervisory functions as external sources of information to help calibrate the harmonizer, preventing it from overfitting to the responses of the language learning model, LLM. To understand the importance of these external sources, we can look at the LLM distilled model columns in our table. Without the supervisory functions, the harmonizer's calibration ability fluctuates due to overfitting to the LLM. We also examined the effectiveness of different loss scalarizer functions and harmonizer model types across all 3 LLMs and 4 tasks. Our table shows the expected calibration error, ECE, and R-squared measure for these different combinations. We found that the best calibration ability comes from pairing a nonlinear quadratic loss scalarizer with BERT fine-tuning. For simpler models like multilayer perceptron, MLP, and logistic regression, LR, a simple linear scalarizer works best. However, the Chebyshev or Max scalarizer performed poorly in almost all cases. These results support our theorem that a Pareto loss scalarizer, as defined in our definition, is necessary to approximate a Pareto optimal harmonizer. However, our approach does have limitations. It relies on supervisory functions as external sources of information. While these don't need to be perfect, they do need to be of decent quality to yield good results. Therefore, the effort required to create reasonable supervisory functions can be a limitation in practical applications. Our proposed framework is also limited to classification tasks, which assume a finite target space. But in many applications of generative LLMs, the output space is not well defined. Future work is needed to generalize our approach to other problems. Section Summary. The supervision functions act as external sources of information to help the harmonizer model be well calibrated and avoid overfitting to the LLM responses. Without these external sources, the calibration ability of the model is not consistently good. The choice of loss scalarizer function also affects the calibration ability, with the nonlinear quadratic loss scalarizer paired with BERT fine-tuning performing the best. However, creating reasonable supervision functions can be a limitation, and the framework is currently limited to classification problems with a finite target space.